Now, using the same parameters as before, p equals 0.8, cos equals -4, and gamma equals 1, I'd like you to run value iteration to completion. And for the one state over here, A4, I'd like to know what is its final value. Now, you might be tempted to write a piece of computer software, but for this specific state, it's actually possible to do it with a relatively simple piece of math. It's not trivial, but give it a try. So what is the value of A4 after convergence? And the answer is 95. To see, we observe that Bellman equation suggests that each new iteration doesn't change the value. We kind of know that the optimal policy is to go south over here. So let's just do the value iteration for going south. Let's call the value x. And we know that the value x is updated by 0.8 times 100 plus 0.2 of staying in the same state whose value is x minus the cost. This invariance must hold true after convergence. We can now resolve it for x. We get 0.8x equals 76. 76 divided by 0.8 is 95. Finally, I'd like to ask you what is the optimal policy for the parameters we just studied. So I'm listing here all states, A1, A2, A3, A4, B2, and B3. And I'd like you to tell me whether you would like to go north, south, west, or east in any of those 6 states over here. So for each of those, there's exactly one correct answer. It's easy to see that in these 3 states over here, A1 to A3, you want to go east. In the state up here, A4, you wish to go south. In B2, you wish to go north, so as to not risk the 0.2 probability of falling into -100. And in B3, it's perfectly fine to go east. Worst case, you find yourself in B2, in which case you can safely escape the -100 by going north, turn right again, and go down over here. So this is the correct set of answers over here.
Now, we're into the last week, so we don't have time to do a full homework on the natural language unit. But since people were asking about more opportunities to do some programming, I'm going to give you that opportunity. And so what I have here is a secret message, and it's asking you to solve a puzzle and put the answer into this box. Now, to know what answer goes into that box, of course, you'll have to decode this message. And I'll tell you that this message was encoded in what's called a rotation or a shift cipher, also sometimes called a Caesar cipher. And that's where we take each letter and shift it down the alphabet and replace it by another one. So if we shifted by 1, then an A would be replaced with a B would be replaced with a C, and so on until we get to Z, which is replaced by an A. But we've not necessarily shifted this by 1, we shifted it by some amount. And what I want you to do is figure out what makes a good language model and maximize the probability of that language model over all possible shifts, and use that to figure out how to decode this message. And then you should be able to easily figure out the answer that goes in there. You may need to do a web search or something in order to figure it out, but that should be pretty straightforward. So that's problem number 1. Then problem number 2 is a little bit more complicated. In problem number 2, we start with a message like this that's not encoded. It's written in regular plain text, but then I'm going to take this message and put it through a shredder machine, and when I get back is shreds of columns, and it turns out that these shreds were neatly made so that exactly 2 letters show up in each column. If I gave you back the columns like that, of course, it'd be pretty easy to reconstruct the message. But I don't, and what happened is they got all messed around and permuted, and what comes back is something like this, and now you have to decode that. And of course, it would be easy if we only gave you a small message like that. So I'm going to give you a more complicated message, and then I'm going to ask you to decode that message and figure out what question it's asking you and answer the question in this box. And here again, you'll have to come up with some kind of a language model, have to figure out what's appropriate. You may use n-grams over words or over letter sequences. It's up to you which ones you want to use. in the first problem, there were only 26 possibilities, only 26 possible rotations of the alphabet, and at least one of them we can rule out because this doesn't look like regular English, so the 0 rotation we can rule out. So there's only 25 possibilities left. Here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 columns. So 19 factorial possible permutations of those columns. You're not going to be able to enumerate all of them. So you're going to have to come up with some more clever, maybe a greedy approach to enumerating the possibilities, putting those columns together to form high probabilities, and then figuring out what the message means and answering the question. So have fun. You should be able to use what you know about language models to solve this problem, and I hope you enjoy it. And I should say that this is all optional. It's not part of the regular homework, so only work on it if you find that'll be fun and useful for you to do so. Here's how I solved the first problem. I took all 26 possibilities for the possible shifts for the given sentence, generated the sentence according to that shift, and then I scored it according to a probabilistic model. And the model I chose was the unigram word probability model. That is, I went out and I got a collection of words and their probability for each one. I used simple add one Laplacian smoothing to get my probabilistic model. And then for each of the possible shifts, I echoed out the shifted translation of the sentence, and at the beginning of the line, I put the log probability of each sentence, and there's a minus sign in front of that, so the lower ones are the better. And it seems pretty clear here which is the best translation. One really stands out, and that's this one here. Stands out in two ways. One is that the probability is about 100 orders of magnitude better than anything else in terms of log 10 probability. And secondly, most of the words here make sense in English, and hardly any of the words anywhere else make sense in English. We can zoom in on that a little bit to get a better look at it. And so that's, out of all the 26 possibilities, that's the only one that even approximates English. And so it's pretty clear that that's the right one. And it says the first conference on the topic of artificial intelligence was held at Dartmouth College in this year. And if you didn't know the answer to that, you could do a web search and discover that the answer is 1956. For the second part of the problem, here's the reconstruction. I've rearranged the slices and put them back together into the proper order, and it refers to the year in which Claude Shannon published A Mathematical Theory of Communication, which again you could look up and find was 1948. Now, this problem is a lot harder than the first. In the first one, there was only 26 possibilities to consider, so we could just enumerate them all, and no matter what probabilistic model we chose, the answer was pretty obvious. I did word unigrams, could have done word bigrams, I could have done letter bigrams or trigrams, any of those would have worked well. Here, it's harder. We have to figure out some way, because we can't enumerate all the possibilities. There's 19 factorial possible combinations. We have to come up with some search technique that checks along the way how well we're doing. And we could do that by saying, let's start out by looking at a few strips that go together best. And one technique might be to say, take all triples of strips. There's only 19 times 18 times 17 of those. And then evaluate all of them, say maybe by a letter trigram model. And then from there on, try to grow that in a greedy fashion by adding a strip to the right or left, whichever one would be the most probable one to add. And techniques like that would tend to work. They may not be perfect, but again, here